All right, welcome to the last example from this lesson. Here we're going to see how to use factoring to solve some of the trickier trigonometric equations that you'll see in pre-calculus and later on in calculus. So we have tangent x sine squared x equals 2 tangent x. Notice that we have trigonometric expressions on both sides of the equal sign. Can't do any math with that. We really need to get all of our trig expressions to the same side. So let's make that as a note. Step 1. Bring all trig expressions to the same side of the equal sign. And in example 2 of this lesson, we then collected like terms. You're going to see that we can't do that in this case, but let's give it a shot and see what we get. So let's minus 2 tangent x on both sides. Minus 2 tangent x on both sides. And these are going to cancel. Now, while you might be tempted to combine these, notice they're actually not like terms. We would only be able to combine them if, let's say, I had 3 tan x, and then I was minusing 2 tan x. Check it out. What's the difference between what you see here and what you see here? The big difference, besides the fact that there was a 3 there, okay, let's get rid of that. There doesn't even need to be a 3. I could still combine these. It would give me negative tangent x because it's 1 take away 2. So what's the difference? Why can't I do it here? You may have noticed that I can do it when I have tangent x plus something else, because now tan is a it's an expression all by itself. Whereas over here, it's attached with sine squared x. It's kind of like trying to add x times y plus x. You can't do it. They're not like terms. So while we can't combine those, what we can at least do is write our new expression, which is tan x times sine squared x minus 2 tangent x equals to 0. So we weren't able to combine to collect our like terms, but check it out. Here's what we can do. At this stage, see how we have a tangent x here and we have a tangent x here? There's a tangent in every term of the expression. So we're going to factor out a tangent x by GCF, or the greatest common factor. So just a quick refresher, greatest common factor is what you use when you're factoring out an x from here. So it would become x parentheses 3x minus 5. So that's what we're going to do in this case. Let's factor out a tangent, since we can take it from both terms. And if I factor out a tangent from, let me underline it, this term, what are we left with? Well, we're left with just sine squared x. Awesome. Now, if we took out a tangent from the second term, what are we left with? Well, we're left with a negative 2, and that's it. The tangent x is out of there. So set that equal to 0. And now this is where we get some really cool algebra happening. By the zero product property, if I have 2 expressions that multiply to equal 0, that means that each expression can equal, one of the expressions must equal 0. So recall, let's say I had 3x parentheses x minus 2 equals 0. Your next step would be to set each factor equal to 0, and then you would solve. So hopefully that comes back. Let's call it right now. Let's label this step we're about to do. So step 2 was factor. We use greatest common factor. Now in step 3, we're going to use the zero product property and set each factor, or each piece that's being multiplied, there's factor 1, there's factor 2, equal to 0. So similar to our example from squaring, where we had tan equaling the positive and tan equaling the negative in our last example, we're also going to have two separate equations here. So our first equation is tangent x equals 0, and our second is sine squared x minus 2 equals 0. I'm going to go ahead and move this because I need a little more room than I thought. So let's first deal with equation number 1, and then we'll deal with equation number 2. Equation number 1 says tangent x equals 0. Remember, tangent represents y over x. So if I want y divided by x to equal 0, that means that just y needs to equal 0. Just the numerator must be 0, because 0 divided by anything is 0. So if I want this fraction to equal 0, that means that the numerator has to equal 0. Well, where is y equal to 0? Y will equal 0 on our unit circle on the x-axis. Over here at 1, 0, right? Imagine that's our circle. So over here we have 1, 0, that's our x and our y. And also over here at negative 1, 0, that's again our x and our y. So I'm just proving to myself that these are the two places where y equals to 0. Therefore, my answers are, well, measuring always from the positive x-axis to the positive x-axis, that's 0 degrees. For our second angle, we're measuring from the positive x-axis to the negative x-axis, that's 180 degrees. In our last step, we'll convert these to radians, and our answers are 0 and pi radians. And part 1 is done. Now let's do part 2. Our second equation here, sine squared x minus 2, is kind of a cool example because we just learned how to do this actually. When we have a square, we learned something in our previous example. So I'd like you to pause the video and see if you can recall the steps that we learned about how to solve when we have a square in our trig expression. There is something that a lot of students forget. That's your hint. Okay, so first I hope that you paused the video and gave it a shot. Your first step would be to isolate the trig expression by adding the 2 to both sides. Next step, you'll want to square root both sides. So you would get sine x equals to plus or minus radical 2. From there, you realize that you have 2 separate equations. Wild, I know, that's 3 total now. But yes, we do have 2 separate equations, so I hope that those of you who caught that, really good job. Sine x equals positive radical 2 and sine x equals a negative radical 2. And then last step, let's figure out where on the unit circle this could be. So remember, sine represents our y value. Now the question is, where is y equal to positive radical 2? I'm going to give you a chance to think about it. Pause the video if you need more time. This was a tricky one, and here's why. Y can be positive. I hope that you at least realized it couldn't be below the axis, right? Y's are positive above the axis. But y actually never equals radical 2. The answer for this expression is does not exist. There is no angle that if I took sine of that angle gives me radical 2. It just doesn't exist. Can you see why? Well, on our unit circle, what's the highest value? What's the highest y value that we reach? The highest y value we reach is 1. Radical 2 is something like 1.3 or 1.4 or 1.5. I'm not exactly sure right now, but it's definitely bigger than 1. So I'm going to call it 1 point monkey, monkey meaning anything, and I'm not exactly sure what it is. But 1 point monkey is out here somewhere. That's outside of our unit circle. The answer then is does not exist. So remember, sine theta will always be between 1 and -1. Same for cosine theta. Will always be between 1 and -1. Radical 2 is outside of that range, so does not exist. Same actually with the second part of this. Negative radical 2 is down here somewhere. Again, our y values never reach that low. The lowest y value we reach is -1. So this gives me a solution that does not exist, and this expression, by the same logic, gives me a solution that does not exist. So my only answers to this entire problem were 0 and pi. Pretty cool.